a solution. It's a process where we're going to use a known solution to figure out an unknown solution. So here's like the technical definition. A solution of accurately known concentration, we call that a standard solution, is added gradually to another solution of unknown concentration until the chemical reaction between the two solutions is complete, used to calculate the concentration of the unknown solution. And this chapter we're looking at acid-base titrations. So the type of chemical reaction we have is an acid-base neutralization. All right. So at the equivalence point, that's when the amount of acid equals the amount of base that's in my solution, and they've neutralized each other. So we could think of that as moles of acid equals moles of base. We could also think of it a little more accurately, would be moles of H positive equals moles of OH minus. All right? Moles of the hydrogen equal the moles of the hydroxide. An easy way for us to think about this is molarity times volume. We talked about in a previous section on molarity, we talked about how molarity times volume equals our number of moles. Right? We can think about the units here. The units of molarity are moles over liters, and our units of volume are liters. So when I multiply those together, I get my moles. So this is the molarity and volume of my acid. I'll get that for my acid, and same thing for my base. So really what this is a stoichiometry shortcut that we only use for acid-base neutralizations. And we'll see why in a little bit. How do we know we're at the equivalence point? We're going to use an indicator to tell us that. Indicators are substances that have distinctly different colors in acidic and basic media. Easy way to think about this is think about like testing with your pool chemicals. Yeah, the pool chemical kit, those will change colors based on different levels. One of those is pH. Right? So we have all these ones that change at different pH levels. Neutral is 7. Right? So what we're going to do, we're going to pick a chemical, an indicator like phenolphthalein. All right. Why? That one is clear or colorless in acidic solutions and pink in basic solutions. So when we're doing a titration, you're going to have an acid. Here, we'll put acid in your solution with the indicator, with the phenolphthalein, and we'll have a base that we're adding to it. All right. As the base gets dropped down into here, it gets neutralized by the acid. Over time, you start to build up, especially right where the base drops, you'll get an area that is basic, so we'll see that pink color show up. Then we'll swirl our flask, and the pink color will disappear as acid comes in and neutralizes the base. Eventually, there's no more acid in there to neutralize the base, and our solution stays pink because now it is a basic solution, or it's been neutralized. Right. When that color changed, that's called the endpoint for our indicator. So the definition of endpoint is the pH at which the indicator changes color. For phenolphthalein, usually very close to the equivalence point. We always want to pick an endpoint close to the equivalence point. The equivalence point has to do with the chemical reaction, has to do with that neutralization reaction. The endpoint has to do with the indicator. So the indicator, we want an indicator whose endpoint is close to the equivalence point. And phenolphthalein is good for most titrations because we're talking about a pH or a change right around where neutral begins. All right. If we looked at the sample on the left, that is a good endpoint. We have a nice light pink color. That means we've added just enough base to neutralize the acid that was there. And now we can do our calculations and figure out and standardize our solution. On the right, that's a bad endpoint. We've overshot our endpoint. We've added too much base to our solution and it turned too dark of a color. So now any calculations that I do, I'm using my volume of my base that is too large. Right. I should have stopped adding the base when I had this nice light pink color. All right, here's a titration problem. All titration problems are mole-mole stoichiometry problems. We use this MAVA equals MBVB as a shortcut. All right, but all we're doing is these can all be solved through stoichiometry, and this is just a shortcut. This MAVA equals MBVB. All right, in a titration, it takes 45 milliliters of NaOH to completely neutralize 32 milliliters of 0.5 molar HCl. What is the molarity of the NaOH? So let's plug numbers into my MAVA equals MBVB. All right, I have a molarity of my acid. I know HCl is an acid, I recognize that. And a volume of my acid. I have a volume of my base, NaOH. I recognize that as a hydroxide, as a base. And I'm solving for my molarity of the base. Again, keep it as MB so you know what you solved for. All right, I can now solve for MB and I get 0.35. So now you're thinking, hey, isn't molarity moles per liter? Why did you use milliliters there? If I have milliliters on both sides, I can keep them as milliliters. And the reason why is, what would I do to this 32 milliliters to convert to liters? I would divide by 1,000. What would I do to this 45.5? I would divide by 1,000. That's doing the same thing on both sides of the equation. Those would cancel out, so I can keep it. If I'm ever calculating a molarity when I have a moles in a liters, it always has to be in liters. I can't use moles per milliliter. That's something different. I need moles per liter. But if I have milliliters on both sides of the equation, I'm good. All right, let's look at another example. All right. KHP, potassium hydrogen phthalate, is a solid acid that's often chosen in standardizing basic solutions. Really, really common acid to use for standardizations. Let's break down the name for a second. KHP. That is not phosphorus. That has to do with our phthalate ion. All right. So potassium. All right, I got my potassium there. Hydrogen. I have hydrogen right here in red. Phthalate. That's this big spaceship looking thing is our phthalate. If I knew a little bit about organic chemistry, this right here is my COO group, COOH. Right at that junction there of those 4 lines, that's a carbon atom right there. So that's my COO group. That's why this acts as an acid. This hydrogen can ionize, forming H positives, making it acidic. All right. This is a solid white powder. You dissolve it in water and you use that as your acid for your solution there. All right, KHP, so we have that. If 14.7 milliliters of NaOH, so that right there I already know is my volume of my base, right, are required to neutralize 0.388 grams of KHP. What is the molarity of the NaOH solution? Oof. So this one's different. Normally, I have molarity of my acid and my volume of my acid. When I multiply together, I get my moles of acid. Here, I have grams. Let's think back to just basic stoich. Basic stoichiometry says, well, I can take these grams and just convert to moles, right? If I take these grams and convert to moles, that bypasses that MAVA step because I get moles a different way. It's still the same number of moles. It's just a different way to get that. And I can still set that equal to my moles of base, which is MB VB. All right. So all this is taking my grams of my KHP, using the molar mass, I can get my moles of KHP. Right? That's my moles of KHP. That's my moles of acid. That has to equal my moles of base. So that's going to equal my molarity times my volume. Now my volume, I switched over to liters because it wasn't milliliters on the other side. So I had to be in liters. So now that I have this, I'm going to divide both sides by this 0.01147 liters. And if we just think about units for a second, those units cancel out. And I'm left with moles per liter which is our molarity. All right. So I was able to calculate my molarity based on the moles of the acid. How did I get moles of acid? I just used grams to moles, a basic conversion of using the molar mass. All right, last one here. How many milliliters of 0.2 molar HCl are required to neutralize 15 milliliters of 0.15 molar solution of BaOH2? All right, pause the video, try this one. All right, this one looks simple. This looks straightforward. But what we probably didn't factor in is BaOH2. There's two OHs there. All right, thinking back, we kind of skipped this slide, but let's go through it for a second, and it's going to help us with this one. If I have, oops, sorry. Let's go, I want my pointer here. If I dissolve two HCl's in my solution, I'm going to need two NaOHs to balance that off. That neutralizes. That's a one-to-one relationship, right? I just showed 2 to 2, but it's a one-to-one relationship ratio. Let's look at this one. If I have an H2SO4 dissolved in my solution, how many NaOHs do I need? I need 1, 2 to neutralize that. All right. Thinking about stoichiometry, I need 2 H's for every one. I'm sorry, I need 2 NaOHs to balance out an H2SO4. And that's what we have to think about in this last problem here. All right. In BaOH2, there's 2 OHs. So the easiest way to factor this in is to say, if I have 0.15 molar BaOH2, every time I have one BaH2 dissolves, I get 2 OHs. So the concentration of OHs is 1.03. We said earlier, a better way to think of this, instead of moles of acid, moles of base, I'm sorry, molarity of acid equal, moles of acid equals moles of base, MAVA equals MBVB, is to think about really it's our H positives equaling our OH minuses. All right. So we're still going to plug everything in the same way, except we factor this OH, and we're going to double our concentration of our VA, OH2, for the hydroxide ions, and then I can solve it and get 77.3 milliliters.